Okay, so the next speaker is Sakuntala Chatterjee from SN Bose Center, Calcutta, and she's going to talk about vacancy-induced phase separation couple-driven system.
I begin by thanking the organizers for organizing this very nice meeting and also for inviting me here. So the title of my talk is Vacancy-Induced Phase Separation in Couple-Driven System. This work is done with Chandradip Khamrai, who is a PhD student at SN Bose Center where I work. And it's not on? Okay, so what are couple-driven systems? So these are just two or more non-equilibrium systems whose time evolutions are coupled to each other. And depending on the nature of the coupling, such systems often show very interesting behavior like existence of metastable states, or sometimes the coupling parameters can be tuned such that the systems show order-disorder phase transitions. Sometimes when you have multiple conserved quantities present in the system, then using the tools of nonlinear fluctuating hydrodynamics, people can identify some unconventional dynamical universality classes, etc. So what I wanted to describe here is a specific model of couple-driven system which we have studied. And mainly, I wanted to discuss various different types of ordering which are observed there. Particularly, we discover a very new type of ordered phase, which I want to focus on. Before coming to the model, I will just spend maybe 1 minute on the type of physical systems where the model that we are studying might be relevant. So there is a very pretty well-studied biological system where people look at movement of certain proteins on cell membrane. So for cell membrane, you can think of it as like a flexible object whose shape can fluctuate with time. Like in this cartoon, I have shown one particular shape. Then these red and blue particles, these are like protein molecules which remain bound to the membrane and they move on this membrane. And these protein molecules, they have this preference for a particular type of membrane shape. Some molecules want to go towards that part of the membrane which is convex. Some other types of molecules want to localize in some part of the membrane which is concave. So therefore, the membrane shape guides the protein motion. Not only that, the proteins also have the ability to modify the local shape of the membrane around their position. So as a result, this is a system where both are affecting the time evolution of each other. And what we were studying a very simple model. The model, it does not take into account all the details of interactions present in this biological system, etc. It's a simple model motivated by this, where we would like to capture the competing influence of different moving species on a membrane or landscape whose shape is changing with time. So this is the model. So we have a one-dimensional lattice whose sides are occupied by either a light particle, yes?
You are saying that some proteins prefer going towards the convex curve, towards the concave thing. So is there some underlying chemical?
Yes, there's a lot of chemical, biological, everything. We don't want to go into that in this talk.
So is it something like that some chemical reaction governs the curvature of the membrane and accordingly the...
So proteins modify the curvature of the membrane. There are some chemical reactions because of that. Proteins prefer certain membrane curvature because of some energy minimization principle. Okay. But we don't take into account any of that. The model we have is very simple. Just more, such that it does not appear very strange model. I gave a physical example where it might be relevant. So it is a one-dimensional lattice. Each site can be occupied by either a light particle, which we call L, or a heavy particle, which we call H. These names will be clear later on. Or this site can remain vacant. So particles are hardcore, so each site can have either one light, one heavy, or no particle at all. Then the lattice bonds can have two possible orientations, plus or minus pi by 4. So therefore, this is one typical configuration where I have specified the site occupancies and the bond orientations. We use different colors. Heavy is shown by red, light is shown by yellow, and vacant sites are shown by blue. And then this is a typical orientation where the site occupancies are specified and bond orientations are shown. And this can be mapped onto a height model where you just join the bonds end to end, and this gives rise to a height profile. We call it a surface or landscape. And height at a particular site H is defined like this. Here tau j plus half is the orientation of the bond between j and j plus 1 at site. It is +1 if the bond has a plus pi by 4 orientation. It is -1 if the bond has a minus pi by 4 orientation. And you just sum it over from j from 1 to I minus 1. That gives you the height at the site I. So this is a configuration. Time evolution of this configuration shows how particle movements are affected by the surface, and surface dynamics is affected by the local particle occupancies. So first I will describe the transition rules for the particles. Particles move from one site to a neighboring site by sliding along the in-between bonds. And here the name becomes clear. Heavy particles or H particles, they prefer to slide downward. Light particles or L particles prefer to slide upward. So for example, if there is one heavy, one light, and this is connected by a downslope bond with a minus pi by 4 orientation, then these two particles can interchange position with a rate half plus A. A is some non-zero positive value with value in this range. And then the reverse transition happens with a rate half minus A. So therefore, heavy particles prefer to slide downward. And similarly, light particles go upward. Similarly, if a heavy particles encounter a vacancy in the neighboring site, that also can exchange position with a similar rate. Light particles can also encounter a vacancy and preferentially go upward with a rate half plus A, and the reverse transition happens with a rate half minus A. Okay. So therefore, it is clear that the bond orientation or the height gradient of the landscape actually affects the particle motion. And this is the transition rules for the landscape or the surface. The surface evolves by interchanging the orientation of neighboring bonds. So if you have, let's say, one downslope, one upslope, it can interchange position and become upslope, downslope. We also call them local valley and local hill because of the shape. And this rate depends on which particle is present at the intervening site. If it is an H particle, then a local hill goes to a local valley with a rate half plus B. The reverse process happens with a rate half minus B. For L particle, the rates are half plus B prime, half minus B prime. Now, suppose if B is positive, that means heavy particles would make a local hill unstable, would like to push it down to a valley, and then the valley is relatively more stable. So here the heavy particles themselves want to slide downward and also want to push the surface downward. So this is called the case of an aligned bias, if B is positive. If B is negative, then the opposite thing happens. Heavy particles want to go downward, want to sit at the valley, but then they are making the valleys unstable. That is called the case of a reverse bias. So particles are pushing the landscape in an opposite direction of their own preferred motion. Yes.
When there is acceleration between high and low, there is the same rate.
Heavy and light, yes.
Heavy and light. And there is the same rate for
yes.
vacancy, in the presence of
Yes.
vacancy. So why you are assuming this?
This is just this is how we had modeled it. I mean, the heavy particle doesn't distinguish between whether it is a light particle or whether it is a vacancy. Yeah, you can include another rate, but for the simplicity, we tried to keep the number of parameters low. Okay, so for the light particles also, positive B primed means light particles are pushing the surface upward in their same preferred direction of motion. That is called an aligned bias, and if B primed is 0, the light particles exert a reverse bias. And vacancies exert no bias, because for vacancy, local hill-valley transitions happen symmetrically. So this is the model. First, I will explain in absence of any vacancies. Another thing I forgot to mention, I think we call this model LHV model, okay, light heavy vacancy model. So when we have no vacancies present, we just take away all the vacancies. So each site can be either an L particle or an H particle. Then we have LH model. This model reduces to LH model, which was actually introduced almost 10 years back, and different phases were studied in detail. So I will just give a brief overview of these phases, and then I will come to the phase diagram for the LHV model. So this is the phase diagram of LH model in the B primed plane. What is B prime? The bias coming from the different particle species. So as you can see, there are many different phases present, shown in different colors, etc. And these panels, they actually show representative configuration of the system from each phase. But if I ask the question, before getting into all the details, is there a single criteria that explain all the phases? And that criteria is as follows, that aligned bias promotes ordering while reverse bias destroys it. So this is, what does this mean? Suppose a light particle, it wants to go up. Therefore, it is most happy when it is sitting at the top of a local hill. In addition, if it also makes that hill stable, that means it's some kind of a positive feedback. Then more light particles can come, they can really give rise to a very, sharp hill, which will attract more particles. So this kind of aligned bias promotes long-ranged order. On the other, A is fixed, A is fixed, something between 0.5. Okay, so similarly, if it is for the reverse bias, light particles want to go to the hill, but when they reach hill, they are making that hill unstable. So this way, no long-ranged order can form. So this is the principle, aligned bias promotes ordering, reverse bias destroys it. All the phases can be now explained as a competition or cooperation between aligned and reverse bias. So first, let us look at the first quadrant, where both B primed are positive, that is, aligned bias is coming from both heavy and light particles. So here, this is the, I don't know if the colors are clear. I don't think colors are clear. Anyway, so here, we call this phase strong phase separation, or SPS, where all the upslope bonds in the landscape are completely phase separated from the downslope bonds, which gives rise to one large hill and one deep valley. I call deep valley because I have periodic boundary condition. And all the L particles are present at the top of the hill, and all the H particles are present at the bottom of the valley. This is the highest possible order that can form in the system. Upslope, downslope bond, complete phase separation, heavy light particle, complete phase separation. This is, when do we find this? When both particles are showing aligned bias. Then come to these lines, when one particle is showing aligned bias, but the other one is not showing any bias. So here, this is the phase. Here, we have here shown the example where L particles are showing aligned bias and H particles are neutral. So there is still a hill, sharp, clean hill, and the L particle is sitting at the top of the hill, but the landscape beneath the H particles are now as not a clean valley like this. In fact, since H particles are not biasing the landscape here, this landscape is showing Edwards-Wilkinson fluctuations, and in an open system, like on one side, it is connected to a reservoir of upslope bonds, and on the other side, it is connected to a reservoir of downslope bonds. So such a system actually supports a current which is proportional to the 1 over the system size. This is known. And so there is a surface current that flows through the system which is proportional to 1 over n. This is called infinitesimal current with phase separation. Then come to the yellow part of the diagram, where this is time remaining, right? Okay, yes. So the yellow part of the diagram where one particle shows aligned bias, the other species show reverse bias. However, aligned bias is stronger than reverse bias because I am above this line, b plus b prime is equal to 0. So b plus b prime is positive, so aligned bias is stronger than reverse bias. Then I still have a phase separation of L particles which are showing the aligned bias. There is still a hill, but this hill is somewhat rugged. It is not a very sharp hill as seen in these two phases. And the landscape beneath the H cluster is disordered. It is called a, there is a finite surface current that flows through the system. The whole landscape now moves upward with a finite speed. It is called finite current with phase separation. Then finally on this line, b plus b prime is equal to 0. When aligned and reverse bias exactly balance each other, here the both light and heavy particles push the surface in the same direction in the same rate. Because light particles align bias, so they are pushing it up. Heavy particles are showing reverse bias, they are also pushing it up. And on this line, the rate becomes same. Another way of saying this, the surface doesn't care if it is a light particle or heavy particle, it will still fluctuate in the same rate. So the coupling effectively becomes one way now. And this is called, this phase was studied for last 25 years almost. It is called fluctuation dominated phase ordering. Here the landscape is disordered and L particles try to cling to the local hills, H particles try to present at the valleys. But since hills and valleys are fluctuating, so these clusters are breaking up, then forming again elsewhere. So this phase is very interesting. It was very well studied, and in this talk we are not going into the details of it. Finally, below this line, when either aligned bias is weaker than reverse bias or both particles are showing reverse bias, like in the third quadrant, everything is disordered. There is no long-range order present in the landscape or in the particles. Now, we are interested what happens when we have vacancies introduced in the system. Intuitively, it might seem that vacancies do not impart any bias, so therefore they should not affect the competition between aligned and reverse bias, and therefore the same phases should hold. But it turns out that is not true. LHV model now has a very different phase diagram, and presence of vacancies actually give rise to very different type, new kind of ordered phases which was not seen before. Okay, so this is the phase diagram for the LHV model. I will now explain these phases. So in the first quadrant again, I have a very clean ordered state when both particles are showing aligned bias. Only difference is the vacancies now present themselves in between light and heavy cluster. Okay, so in landscape is again very cleanly ordered, and all the L particles, vacancies and H particles are separately ordered. Same thing happens for the IPS phase also, that everything else is same, vacancies just insert themselves in the in between H and L cluster. But when we come to this yellow part of the diagram, when one showing aligned bias, another is showing reverse bias, then we have a slightly different phase. Here the particle species which show aligned bias is still phase separated. But in the remaining part of the landscape, which is flat, disordered, the heavy particles and vacancies, they are mixed together. Okay. So again, same current flows through the system. It's called a finite current with partial phase separation. Partial because only one particle species is showing phase separation now. So these are some, so here I have plotted, I have measured the distance from the center of mass of the L particles and I have plotted the density profile. So you can see the L particle has density 1 in this region and then it drops to 0, and holes and heavy particles have density 0.5 each. And here I have plotted this probability S plus R, which is the probability of finding an upslope bond at a distance R. And as R changes sign, the probability drops from a high value close to 1 to a low value close to 0. This is because consider two arms of the hill. On this arm, there is a high probability of getting upslope. Similarly, on this arm, there is a very low probability of getting upslope. So S plus R drops rapidly. And if I integrate S plus R, I get the average height profile, which looks like this, which is here the height of the hill that scales as n actually. Another thing is that notice S plus R is slightly less than 1, slightly greater than 0, which means the hill is rugged. This is why it is so. So next I wanted to calculate the phase boundary of this FPPS phase. So we had seen that there is a large hill, and let lambda be the fraction of the minority bond type present in each arm. So in the rising arm of the hill, it is mostly upslope, but I assume there is a small density lambda, which is density of downslope bonds. So clearly lambda should be less than half for the hill to exist. Now, this is a local configuration. There's one upslope, one L particle, another downslope. So the local hill occupied by an L particle. Let P be the probability to find such a local configuration. Then this probability times half minus B primed gives the flux of probability for this hill to valley transition. And similarly, the reverse transition is associated with the probability flux half plus B times P of probability of this other local valley, microscopic valley occupied by hill, this configuration. And the difference between these two probability flux will tell me the current that is flowing through the system. So this is the surface current. And now I don't know what these correlations are, so I will use mean field approximation. I will assume that this factorizes. Density of L particle is 1 here, and then probability of finding a local hill or local valley becomes lambda times 1 minus lambda. So this is the surface current flowing through the hill. What is the surface current flowing through the disordered segment? Disordered segment have heavy particles and vacancies, but vacancies do not impart any bias. So therefore, the contribution of current only comes from the heavy particles. So this is the current, and this is using mean field approximation, this takes this form. And in steady state, both these currents must match. So when we do that, we find a quadratic equation of lambda. We can solve that, and this is the solution. Now for the large hill to exist, lambda should be less than half. That is, this part should be positive. So this gives me the equation for the phase boundary of this FPPS phase. Okay, so at the phase boundary, lambda is equal to half, and beyond that, if it falls below that, then the hill cannot sustain. Notice another thing, that if I now put if I now take away all the vacancies, then it goes back to LH model. In LH model, 1 minus rho L is equal to rho H. So I am getting back this line, B plus B prime is equal to 0. So I am getting back this FDPO line. Notice another thing, and this is very interesting, that I can suitably choose rho L and rho H such that I can have long-ranged order even when aligned bias is weaker than the reverse bias. This was not possible in the LH model, but now we are introducing vacancies, and now the system can sustain long-ranged order even when reverse bias is stronger. What is happening here is that if you go back to the typical configuration, these L particles are pushing the landscape at a slower rate, and the heavier particles, H particles, are pushing it faster because reverse bias is stronger, but the vacancies are mixed with the H and they are not putting any bias. So the effective upward pull coming from this disordered sector is reduced because vacancies are present. And this gives the aligned bias a chance to fight with the reverse bias and win over it, and the long range order is still maintained. Okay, so so this is a new effect of introducing the vacancies, that even though aligned bias is weaker, it can effectively reduce the reverse bias such that long range order is still there. But this cannot go on forever. When the reverse bias becomes very strong, then even though all the vacancies are present, it is still not enough to let the aligned bias win. In that case, the hill cannot sustain anymore, So however, that does not mean that this phase separation is lost, the ordering is lost. So in this case, what happens, if I go back here, yeah. So suppose I still start with such a configuration, then this part moves upward at a higher speed and catches up with the hill. And the hill cannot sustain anymore. But, so what happens then, some small number of H particles, some small fraction of H particles roll into the L-dominated region, and this way the system can balance current. So in other words, L particles still phase separate, but it is not a pure phase anymore. A small but finite density of H particles are present in it. And the remaining heavy particles are present mixed with the vacancies, and this makes sure that the current is balanced everywhere. This is a new type of phase ordering. We call it vacancy-induced phase separation, or VIPS. So this is the, here I have shown the density profile. You see that L particle density is now less than 1, but the fact that they are phase separated is very clear from this plot. And we have also plotted the 2-point density-density correlation for the L particles. And for large system size, the correlation function shows a scaling collapse if you plot it across R over N, which shows existence of phase separation. For small system size, we do not find scaling collapse. In fact, even when system size is not so small, we find that it is still, the finite size effects are quite strong here. But even then, we can extract some macroscopic length scale, like we can find out at what distance the correlation function crosses 0 for the first time. And that distance scales linearly with the system size. This is the, sorry? Just the LL correlation, density, 2-point density. Average value I have not subtracted here. That is why this is the 0 crossing. So, yeah. Okay, so, yeah, so this shows that the particles are, L particles are still phase separated. And what happens to the landscape? The landscape does something very interesting. We have discussed that the hill cannot be present here anymore. So the landscape takes the shape of a plateau. Okay. So L particles are phase separated, still at an elevated zone, but with a flat hilltop. So it's like a plateau. And the height of that plateau actually scales as root n for large n with the system size. And so this is the new phase, VIPS phase, that particles showing weaker aligned bias, still phase separated, not a pure phase, but a clean phase separation anyway. And it is present in the top of, on the top of a plateau. Yeah, so we can also now estimate what is the fraction of the H particles present in the L phase, to what extent it is pure. Remember why it went there? Because L's are pushing the landscape upward at a slow rate. H's are pushing it at a very high rate. So now few H is coming, mixing with the L. This mixture has now an enhanced upward pull, and the rest of the H is now mixing with the vacancies to make the balance. Now, let F be the fraction of the H particles present in the L phase. We tried to estimate F here. So this is the upward surface velocity coming in the plateau region. Different hill valley transitions governed by H and L particles. And in the plateau region, we assume that it is equally likely to have upslope, downslope bonds. So within mean field theory, this is just 1/4. So using mean field theory, this is the form of the current. Similarly, current in the disordered sector has this form, and when we match the two in steady state, we get this expression for the fraction. When we compute it with our simulation, we find that, okay, at large n, at small n, the gap is really large, but even when n increases, there is a significant gap. It could be because, most probably it is because we have used mean field theory, which is not working here. However, this expression that is not completely useless. If you put f is equal to 0, you get this equation back, which is the equation boundary line between FPPS, VIPS phase. So exactly on the boundary line, when the hill has just started crumbling down, L phase is still pure, but as you, so let me go back to this phase diagram once more. Yeah. So exactly on the boundary line, L phase is still pure, but as I am going deep inside the VIPS phase, the difference between aligned bias and reverse bias grows larger and larger, and a larger fraction of H particles need to be present to balance the steady state current everywhere. And finally, in this disordered part, this third quadrant, when both the particle species are showing reverse bias, that is the only case when you have a disordered system. So in short, introducing the vacancy actually makes it easier for the system to create long-range order. And now the disordered part is pushed down to only strictly the third quadrant when both are showing reverse bias. As long as at least one particle is showing aligned bias, does not matter how weak it is, there is still a phase separation. There is still a long-range order. One last thing. Yeah. So we also tried to estimate the finite size effects in the VIPS disordered phase boundary. As we said that the system shows strong finite size effects here. So what we have done here, we have measured the subsystem density fluctuations. So we put a box of size S, which is much larger than 1 but much smaller than the system size. And then we calculate the number of L particles present in that box. That number will fluctuate, and we calculate the variance and see how this variance scales with the box size. So if it was a homogeneous system, then variance will scale linearly with the box size, alpha is 1. On the other hand, if it is a perfectly clustered state, then variance will scale as S square, alpha is 2. So as alpha makes a transition from 1 to 2, that can be taken as an order disorder transition. So here we plot alpha as a function of the strength of the aligned bias for a fixed value of the reverse bias. And we see that for large, as n increases, the transition becomes sharper and also it shifts towards the zero align, B prime is equal to 0 line, which is what we have shown in the phase diagram. Okay, so I finished before time. So this is the summary. One point here is that we used mean field estimates, which were not accurate in many cases. Actually, that can be improved upon. In a previous work, we had shown that it is possible to choose a relative time scale between the surface dynamics and the particle dynamics, and you can tune that time scale to make sure that the product measure is satisfied in the disordered sector. So that was shown for LH model, but in the disordered sector, only 2 species are present, heavy particles with vacancies. So that is effectively one LH model because only 2 species are present. And there actually, it was possible, we could show that a time scale can be chosen such that this satisfies product measure. This can help us, then the mean field theory becomes exact. But here, although we have used same time scale just to keep the model simple. Okay, so with that, I would like to thank you for your attention and if there is any questions.
Subject?
Yes, I was wondering, like, is it possible to write some like hydrodynamic equations for the 3? You have 3 fields, right?
Yeah.
I mean, did you do that? I mean,
so in the, for example, in the LH model, it is possible to do it in the disordered sector.
yes, the disordered sector. Right?
Yes, in the disordered sector, you have 2 conserved species here, particle density and slope density.
Right.
So these are coupled. So then you can use nonlinear fluctuating hydrodynamics and you can calculate various different dynamical universality classes. This we had done.
Okay.
For this 3 species case, we have done it, but then, it is possible to do it for the 3 species case, but what helps for the 2 species case is this, what I was saying of the relative time scale, which actually, if possible, you can find some product measure where this because we don't have current density relationships exactly. We were using mean field theory,
Okay.
but then if you can use product measure, then those can help. Here actually this, when all the species are present, then this relative time scale thing doesn't work. We could not find anything yet. So, but in principle, what you're saying, one can write down the hydrodynamic equations for the disordered pattern.
Like in the this disordered phase,
In the disordered phase, yeah, in the disordered phase,
like the space-time correlations.
short range correlations are there, which can be pretty strong.
Okay. No, space-time correlations, like,
Okay.
I mean, is it like just diffusive or like KPZ or what?
Yeah, diffusive KPZ we had seen for the 3 species case. For the LH model, there are 5/3 Levy, 3 modified KPZ, 3/2 Levy, lot of different universality classes could be seen. Yeah.
Other questions? So I have a question. I mean, it seems that somehow when you introduce the vacancy, you destroy the FDPO phase,
Yeah.
right? Do you have any understanding why does it happen?
Yeah. Because when FDPO means I need one-way coupling.
Right.
But since vacancies are not doing anything, so the only place where you could find FDPO is when everything is B prime, everything is 0. That is a trivial. That is just an surface fluctuating like Edwards-Wilkinson. That is the only place where FDPO will hold at the origin of the phase diagram. FDPO line is not there anymore.
Yes, with no other questions, thanks. Come back here.